Hi everyone. So today I'm going to talk to you about Git and about Haskell. So this is an iHaskell notebook. If you haven't heard of that before, it's essentially a Haskell backend for the Jupyter kernel, or a Haskell kernel for the Jupyter notebook. So I like it a lot. I help maintain this project, and I love using it for presentations and just doing stuff. So let's look at a Git repository. So I've chosen to use the solarized repository. It's a color scheme. Hopefully you're reasonably familiar with it. So I'm essentially one way of running shell commands in the iHaskell notebook is to prefix that with similar to the way you do it in GHCI. So I'm deleting any copy of Solarize that already exists, and I'm cloning it, and I'm running this command to show you the most recent commit in the raw format. And the -s suppresses the diff output, because Git usually shows you the diff. So this is going to take maybe a minute. Also, if there's anything that's not clear, feel free to stop me at any time and ask. So, like I said. I'm connected to Wi-Fi, right? That'd be very embarrassing. Okay, good. Started. So a commit has, as displayed in the raw format by Git, has a commit hash, a tree, a parent, an author, a committer, and a commit message. So now that I've cloned this repository, I'm going to show you what's in the Git objects directory, which is where Git stores all of its files. And when you clone a repository, Git downloads a large file, because downloading one large file is much faster than downloading a bunch of small files. But when you're operating on a Git repository, you create a whole bunch of little files, little objects. And I'm going to convert the large file into a bunch of small files, because they're easier to work with. If you're curious about so I'm not going to go into the details of the large file. It's called a pack file format too much right now, but there's an article, a really good article on it called, wait, no, what have I done? It's called Unpacking Git Pack Files, and yeah, I've implemented this separately, which I'll get into a bit later. But anyway, so first thing I want to do is I'm going to show you the pack file, and I'm going to decompress it. So Git has a command called git unpack objects, which will take that pack file and turn it into a bunch of small files. So now I can do the same. So when I do a git show, Git also has a command called catfile, which can essentially pretty print or display the contents of any object. And the -p is for pretty print, and head is the most recent commit. So I do that, and I see almost the same output here. And I say almost, I mean because the commit isn't actually shown when I do a git cat file. And the reason for that is that the commit isn't actually stored. The commit hash isn't stored inside the commit. It's a separate thing. Git keeps track of that separately. So otherwise, it's the same, right? We have a tree, a parent, an author, a committer, and a message. So what is head anyway? Head is just a file that lives at .git/head, and now it points to another file. And this is very similar to a symlink, and the reason that it's not a symlink is because Git has to be cross-platform, and symlink support in Windows is not ideal. So now I take that, and I put it in here, and I look at it, and now I get something that's useful. So this is a hash. In fact, this is the same hash that we have up here. Right? So you can use git-cat file to show you the contents of that hash and same content. But what is this hash? Like, what does it mean? So in Git, so what Git does is that it stores it in the objects directory after I've done my unpacking, and it uses the first two characters of the hash for the directory name, and the other characters of the hash, the other 38 characters of the hash for the name of the file that the content lives in. And the reason for this is that there are thousands of files that make up a Git repository. This is a relatively small repository, but large repositories, so even it contains roughly 2,000 files. And if you store 2,000 files in a directory, at least in older file systems, you have so many files in one directory that it would slow down lots of operations. So what Git decided to do is that basically, if you have the first two characters of first two hex characters, that gives you 256 possible directories. And under the 256 possible directories, it's a way of essentially bucketing the files across, so that you don't actually put too much load on one directory. So if I cap the content of it, I get gibberish. And the reason I get gibberish is because this content is compressed using zlib. Fortunately, there's a command called zlibslate that you can use to uncompress some content. So I'm going to go ahead and do that. And I get, again, almost the same content that I did before. The difference is that I have a header. So there's a commit, the word commit, and the length of the content. And there's a null byte here, which you can't see, but I'll show you in a second. That sure, hopefully I convince you that it exists. So far we've we haven't written any Haskell yet, but we're about to. So there's a zlib library for Haskell, and it uses lazy byte strings, but I'd prefer to work with strict byte strings for everything else. So I'm just going to write an adapter, like two adapters, compress and decompress. So I define those. And then I want to read the content just like I did before and decompress it. So again, yeah, sorry, do you have a question? Okay, cool. Yeah, so again, like I said, there's a null byte. So I can read this content, but now I want to start parsing it. So I'm going to use attoparsec. Attoparsec is a really cool parsing library for Haskell. One nice thing about it is that it automatically backtracks. Another thing about it is that it's optimized for byte strings. And yet another really nice thing about it is that it's meant to be really fast. So none of these parsers are going to fail, hopefully. So I'm just going to go ahead and kind of ignore the possibility that they will. And I'm going to parse a header. So if I want to parse a header, all I have to do is parse everything until a space. I parse a space, I parse a number, I parse a null byte, and I return a tuple. So I do that, and I get what I expect. Now I want to parse a hash. So the easiest way to parse a hash is to just parse 40 characters. Like ideally, I do something where I essentially confirm that each of these characters is a valid hex digit, but I don't need to worry about that so much. So parsing a commit is relatively straightforward, right? Given that what I've told you like at least 3 times so far. So a commit has a tree, parents, author, a committer, and a message. And I say parents. The initial commit of a Git repository has no parents, so it's 0 parents. And a commit usually, like a merge commit has 2 parents, but there's no reason you're limited to just 2. You can have more than 2 parents of any merge, and that's known as an octopus merge. So I parse a tree, so I parse the string tree, and then a space, and then the hash, and then the end of the line. Similarly for parents, author, committer, and then the message. So I go ahead and I parse that. So I've turned my commit into data type that I can work with. So if I've deserialized it, but now I also want to serialize it, so I can check that I can round trip. So I'm going to go ahead and do that. So again, I just essentially add back in what I took out, and I do a quick test that if I take my commit, I convert it to bytes, and then I parse it, then I get exactly the same thing that I started with. That's true. I also want to serialize headers. So again, those are much easier to serialize. So I just add that null byte in the space. So do that. So this looks like it's the same content as I got up here, which is good. So now I get to I guess something that's a bit more interesting. So how does Git determine what hash a content is? So Git is a content addressable store, which means that the hash that it uses is just the hash of this content, the SHA-1 hash of this content. So let me demonstrate. So if I take that content and I hash it, I should get the hash that we started with. So I mean, let me see if I can go all the way back up to where we had the hash. Yeah, there. So I mean, it's the same hash. I hope. Yeah. Anyway. So far we've done commits. Let's do trees. So a tree is what Git calls like one level of a directory, a directory listing. So this is what the directory listing of the solarized repository looks like. So it has these numbers, which are a restricted set of Unix file permissions, the type of object that it is. So a blob is what Git calls a file, and a tree is just another directory listing. It has a hash, and it has the name associated with it. So if I decompress the content of the object, I should get the same content, but I don't. In fact, I get something that recognizably like a Git object because it has the header, it has some length, and it has a null byte. It has the number 10644, just like up here. It has the Git modules, just like up here. But instead of a hash, I have this. And the reason for that is that you can store a 40-character SHA-1 hash, a 40-character hexadecimal hash as 20 bytes, and that's what Git decided to do to save space here. So what we need to do is we need to base 16 encode the 20 bytes. So if we do that, then we can define a tree data type. So a tree is just a list of tree entries, and a tree entry is Unix file permissions, a name, and a hash. So I can parse that similar to the way that I parse my content, parse my permissions, I parse a name, I parse a ref. So I can parse a tree just by parsing many tree entries. So I go ahead and do that, and I get essentially the same thing that we got before, just not pre-printed. So that's good. So if I can parse it, I can also serialize it and check that it's serialized correctly. So I've done commits and I've done trees, and I'm going to do blobs. A blob is just what Git calls a file. So this is a changelog, for example. So where did that hash come from? So that's this file. I went and looked at it earlier, and it just doesn't have anything in it. So it's not interesting. But this one, yeah, is a changelog. So that's the one that I used. And I decompress the, so blob is literally just a header attached to some content. So it's not very interesting, not very difficult to parse. You literally just parse a byte string. So as expected, then I can serialize it easily just by serializing it. Like there's really not much work there. And this is the fourth and last type of Git object, which is a tag. So Git has a command that can show you the tags. So I pick the first tag. I go ahead and read the content of it. So a tag is not too different from a commit in the sense that a tag is a way of naming an object, because usually like dealing with hashes all the time can get a little tiring. And sometimes you want to tag some commit, for example, as a release, which is I guess the most common use for them. So this is the SHA-1 hash of the object that we're tagging. This is the type of the object that we're tagging. So tags, you can tag a commit, and that's the most common use case. But there's no reason you couldn't tag a blob, a tree, or even another tag. Although that seems silly. I can't see why you'd want to do that. The name of the tag, the person who tagged it, and the tag annotation. So again, similar to a commit. So if I decompress it, similar to a commit, I can just parse it. I can parse the object, the type, the tag, yeah, so on and so forth. And I can serialize it. And then I can bring it all together. So like I said, there's 4 types of things. There's commits, there's trees, there's blobs, and there's tags. So a Git object is either a Git commit, a Git tree, a Git blob, or a Git tag. If I wanted to parse a Git object, I can read the header and parse accordingly. And if I want to serialize it, I can, again, serialize accordingly. And I can get the hash of any Git object just by hashing the serialized content. So I define that. And what I want now is to just confirm by parsing my tag and then serializing it and hashing it that I get the same hash that I expect. So which is I mean, you can see that it's recognizably the same. So I want to add these. I want to add like these extra path components in. So .git objects, and I put a slash in the right place. So I write a tiny function that just does that. And so now that I've written that tiny helper function, I can write a read object function that just takes the directory and a ref and decompresses whatever's there and does it. So great, that works like I expect. And if I can write a read object function, I can also write a write object function. And this is the most interesting part of the write object function, in my opinion. So if Git has some content that Git already has a file that exists at the hash, it assumes that it's the same content, because the chances of a SHA-1 collision are low, although not 0. So which is why Git is, in fact, now moving away from SHA-1. At some point, they probably adopt SHA-256 completely. But for our purposes, yeah, so it gets the hash of the object, and if there's already an object existing at the directory, it doesn't try to write anything else. So that's one way in which Git saves space. And I've done my read object function, my write object function. Now what I'm going to do is I'm going to take every single object in this Git repository, I'll tell you how many there are. I think it's like 2190, if I'm not wrong. And it's going to read and write every ref and check that they're all equal. And if so, yeah, it should. Yes. So we're done. So that's everything in this Git repository that I've read and written. So this is what I've shown you. What haven't I shown you? I haven't shown you any diffs. So where does Git keep its diffs? It doesn't? Exactly. It doesn't. There are no diffs. whenever you do a git diff or anything like that, it computes the diff on the fly. So I guess that's the thing that surprised me the most when I was working on this, because it's like, oh, of course Git stores diffs. Like, obviously, it doesn't just store every version of every file. That would be silly. But in fact, it does store every version of every file. So yeah, I mean, so that's essentially it. That's Git. I've Haskell to Git. It's there. It's all there. I also have this material available as a blog post in case you want to look at it again or you want to try it. This notebook is also available on my GitHub, and so this work kind of came out of something else that I was doing, which is like a more full-featured Git implementation. Because like I mentioned, this doesn't handle packed files, and it doesn't handle like some other things that you want to do. If you wanted to like create a new so there's quirks to Git, right? So if I wanted to like create a new tree directory, and I sorted the trees in any which order, my trees in any which order, then it's not necessarily the case that the hash will be the right hash, right? So Git has a weird it stores them alphabetically, but it treats directories slightly differently than files. And if I wanted to implement the pack file format, so I've done all of that over here, and gone a bit further and defined things like converting Git objects to JSON, and I called this project Duffer. And the reason I called it Duffer is because I had a Hindi teacher when I was in grade 4, and she called me a duffer in front of the entire class. And if you're Indian, you probably know what that means. It's not ideal, and I've never forgotten that insult. But and so when I was coming up with my project, I was like, hey, I need to name this something good. Like, what's stupider than a Git? So anyway, so and then so what are some of the things that you could do with this? So programmatically manipulating Git repositories is something that's pretty useful. Like, a lot of people do it. I should point out that I'm not the first person to do this, even in Haskell. Yes. So I think this is the best known Git. I think this is the most full-featured Git library. So I knew that it was there if I needed to figure out why something was weirdly broken. And when I was working on this, I also decided that I would use the Git repository itself as the test corpus. So literally, my tests for this library are reading and writing every object inside its own Git repository, which I think is pretty good. Definitely caught a few bugs that way. And I also another thing you could do is that if you wanted, if you can programmatically manipulate a Git repository, you can convert it to JSON, for example. You can read and write JSON which is essentially what GitHub does, right? So I went ahead and implemented something that allows you to serve a Git repository as JSON using my Duffer library. And yeah, so I think of this as basically like ShitHub. So it's like a really, really shitty GitHub. So I've done that. What else? Yeah, and another interesting thing about this is that Git, it basically guarantees that you won't lose data, which is pretty great, right? And I have a background as a web developer, so I was doing web development for a bit, and I would have to handle database migrations. And database migrations, there's a lot of things that I didn't like about web development, but I think database migrations is the thing I like the least, because I would always really be worried that I'd be losing data. And if you do database migrations, I feel like most of the time the guarantee that your database gives you is that we'll keep track of your schema changes. But as far as your data goes, you're essentially on your own. If you lose data, it's too bad. But Git kind of is the opposite, right? So Git has a very simple data format, but that so Git is look, I don't really care about your schema. You can do whatever you want, but I'll make sure that nothing bad happens to your data. And I think that's a much better base to build stuff on top of. So that's another thing that really appealed to me about working on this. Yeah, I guess, what else do I want to tell you about? Oh, yeah. So in OCaml land, they have this really cool library called Ermin, which is essentially a database which is, like I described, it's Git backed. So they have a rope data structure that's diffable, and they use that as the base of their of everything. So in fact, you can kind of take an Ermin database and interact with it using the Git command line tool, because that's how deep the resemblance is. That's pretty cool. I guess that's mostly it. I should mention that I did a lot of work on Duffer at the RICO Center, which is a programming retreat in New York. It's probably my favorite place in the world. If you want to talk about that, I've attended a batch at the RICO Center, but there's a couple other people here at HaskellX who've also done that. I should also mention my lovely employer, who I also have like a bunch of people who are here. I think we're hiring. If you'd like to talk to us about that, please come talk to me or any of the other 4 people here. In fact, my colleague Robert is like giving a talk right now, so I feel like everyone else is there instead of here. It's sad about, but life goes on. I guess that's it. Thank you. Questions, comments, suggestions? Yes. Wait. Oh, wait. Yeah. Oh.
Have you looked at building any of the kind of actual Git tools that use these raw objects, like doing a Git diff yourself?
Oh, I've been actually kind of really wanted to implement like diff logic myself, which is why I haven't gotten around to it, because like diffing is harder than I thought. But actually, now that you mentioned, I did do so I decided that what I really wanted to do is teach people about Git. And one way of doing that is to do a workshop, right? And I was like, oh, how cool would it be if my workshop were also a Git repository? And then I started thinking about what it would take to like actually do all the rebasing or cherry picking every time you make every time I made a change or like an edit. And I was like, oh, it's too much work. But then I remembered that I had a Git library, so I could just write some code to write my repository for me. So in the process of doing that, I did in fact like implement stuff that will do a Git init. So my Duffer library does include things that will just you can like Git init a repository and you can like make a commit with some content. So in fact, I use that, and I have a Git internals workshop. There we go. Yes, so that uses my library to actually, yeah. So yes, I have done that, but no, actually, but I guess the deeper, I think the question is, like, I feel like the deeper question is that actually part of Git? And I've decided that, for now, like the answer is no, because Git is just a data format. Like the Git suite of tools itself is a bunch of bash scripts and C scripts, and C programs and Perl scripts that interoperate with each other. And the only thing that they really agree on is that the data format is the same. So I could, anyone could implement like a diff library and like in Haskell. And the fact that I haven't implemented that, although it's something that I still want to do, doesn't mean that I haven't implemented Git.
Yeah, I'd say don't do it because I've already done it once. So.
Okay.
You might.
Right. More questions? Yes.
I think this would be a very interesting component of a regression testing tool. For example, testing various commits against each other, or against a golden version or something.
Yep. I was talking to someone about this at Lambda Jam earlier this year. He was saying that he had this tool. I'm not sure if it's open source or like if it's just one. It's in a forgotten corner of his laptop called Igor CI, where literally he would do that. He would but I don't think he used I think he just used like the Git command line tool, but he would like check out like different revisions of the repository and kind of even store test results alongside the Git repo. So there's definitely these are the things that these are the kinds of things that having programmatic access to a Git repo enables you to do, which I don't think you would do before, just because it's a lot of work. Like I guess the other thing that I should probably mention is, now that you've seen me do this in 15 minutes in front of you, does Git seem like that scary? It definitely felt much less scary to me afterwards, once I actually knew that, okay, look, if anything goes horribly, horribly wrong, I can just go ahead and poke at the thing myself until I figure out how to undo my change.
Actually, I have another tiny thing. Why is decompress a pure function from zlib?
Oh, zlib it is a pure function. It just takes byte strings and gives me other byte strings. It doesn't actually depend on input or output.
But what if this byte string is not in a zipped format?
Oh, then we'll throw an exception. But I didn't make that decision. But it's not I don't think it's.
It doesn't have a monadic interface.
I think zlib might have a monadic interface, but I think it also just provides just simple compress and decompress functions. And for the purposes of this, so this talk was marketed as advanced, which I wasn't really sure how to fix that, or if it was worth fixing, because it's not advanced, right? My whole point is that it should be as simple as possible. But yeah, so I avoided kind of doing anything really fancy. So I guess the first big change that I would make here is that I would use an environment to like store where my Git directory is, because that's something that like every command needs to know about. So that's like one change that you can make. Another change you can make is like actually implementing like so it is quirky, like the logic for like sorting these entries so that the hashes are deterministic is a bit quirky. The possible values of this, like I said, they're restricted file notation, so it just can't just be any numbers. So these are the most common, but there's like 5 or 6. Again, this is all implemented in my bigger repository, but not in this demo.
Have you taken a look at how Git LFS and submodules implemented in the tree?
I've looked at it briefly. Git LFS, I haven't looked at Git LFS so much, but I think, so one of the original motivations for this is that I was part of this Haskell community. Actually, I wanted to give a talk to this Haskell community in Canberra, where I used to live in Australia. And they were like, hey, we really want to know how Git Annex works because it's implemented in Haskell. So I looked into it, and essentially what it does is that instead of having like 2 directories it essentially does the same kind of thing, but instead of using like one directory and then 38 characters, it uses like 2 directories and kind of stores stuff in its own way and just hashes the binaries. But I think it only stores like 1 or 2 of them, versions of them, instead of like storing every version of everything. That's actually another interesting point. So most people have heard the best practice that you don't store binaries in Git, right? Why is that? Like, can you tell, like looking at this, why that is? Like the reason is, well, one, because Git stores every version of every file. So, and like when it's, so I guess that's essentially it. So instead of storing, if it just stored diffs, then it'd be bad, but not quite as bad as what it actually is doing. So other than that, no, I haven't really looked into Git LFS or Git Annex.
And I noticed you have a type tag, like in a Git object.
Yep.
And many other tools perhaps could use it too to store their own content. And how broken a Git tree will be if you add some custom type?
Oh, that's a good question. I actually don't know. Like, so your question is how, like, so Git, I said Git has 4 types, right? So what if you added like a 5th type? That's an interesting point. I'm not sure. Like, well, definitely this parse would be very broken because it would, choke on the first thing, and I have 0 error handling here. But more interestingly, the pack file format, the file format that like Git kind of stores things into like save space, has like, I think it uses 1 byte to store the type of object that it is. So I think there's like 1 or 2 spaces there that it's reserved. So maybe that could accommodate like an extra type if you decided that there's like, okay, we want to add like a binary type. It's like specifically binary and it's like maybe not tracked or like tracked in a different way. So it's doable, but I imagine like a lot of the C, like a lot of the original implementation is probably operating under the assumption that like there's only 4 types.
Hi, great stuff. You mentioned 2 performance optimizations in there. One about how some data was encoded, another splitting the SHA to make a load of directories to act as buckets. I know Microsoft's been doing a load of work to make Git scale because they've got huge repositories and they like it. I was wondering if you knew of any other performance optimizations they might be doing.
Yeah, there's a ton. So given what I've shown you so far, like how does Git status know like what files have changed? Like the only way that it would know if it crawled like the most recent commit, looked at everything in there, and like looked at what the files were in the working tree, and that makes no sense, right? What Git actually does is that there's another file called the Git index, which literally is just a list of files that it knows about and the time that they were last modified. So it can like just look through that file instead. And I think that's one of the things that even that you can run into problems with if it's similar to the size of one of Microsoft's repositories. And I guess another optimization is the pack file format. I haven't discussed it at all here, but it's a very interesting format. It's very quirky, and they have a lot of like, I think I was reading this blog post where Microsoft was talking about using a bitmap to like optimize instead of like kind of scanning through the whole pack file to like make some common operations work faster or unpack some objects faster. So it's like it's a really deep topic. It's a really fun and deep topic. And like I guess one other interesting thing that maybe I haven't mentioned yet is So because Git stores every version of every file, it's a persistent data structure, and it's if you actually want to like talk about the practical applications of functional programming, this is like it's right here. So it's something that most developers use like every day.
Thanks.
How is the performance of your code compared to the C Git implementation?
Oh, C implementation. Well, I haven't benchmarked the performance of this code because it's a Haskell notebook. But my performance of my I mean, I can't really tell much. I mean, I haven't actually tried to like implement like the command line aspect of it. Other people have done that. There's like this really cool. Well, there's HSGit, but I don't think it has command line stuff. And there's also this really cool, I think Git from the bottom up. So this is really interesting by, no, not this. So yeah, see, it's more than one person has kind of gone down this route. Yeah, there we go. Okay, clone Haskell from the bottom up. So this person, I think he works at Atlassian now, but implemented all of Git, enough of Git, which, like including the network stuff, that they could just do a Git clone, which is pretty impressive. But to answer your actual question, I don't, like for small repositories, it's fast enough that it's not really that big a deal. But where my performance, my implementation really chokes is doing reading through a pack file that's like a few gigabytes large. And I don't think there's any inherent reason that it has to be that way. It's just that I haven't figured out where the bottleneck is or how to fix that bottleneck. It could be a lot better. If you're interested in kind of like poking at why that's the case, I'm very, very happy to accept any all contributions to this.
Cool.
Thank you very much for the talk. Is Git the original blockchain, and when are you announcing your cryptocurrency?
Well, the answer to your first question is yes. The second question is, it's actually a really good question. I always thought that if I could like release my own blockchain and make it so that like the amount of time that your CI servers or your like I don't know what they're called, mining thingies do like CI builds for open source projects is what determines how much money you have. So that's my big idea. Feel free to steal it. Please free to make CI coin or like whatever you want to call it. But actually yes. So Git is technically under the definition of like a Merkle DAG. So because commits can have like, so they're a directly acyclic graph where each commit contains the hashes of its ancestors. So by that definition, it's a valid Merkle DAG, and a Git tree object is a valid Merkle tree. So yes, so I guess if you were like really super interested in like learning about blockchain, but also really wanted to learn about Git for some reason, it's a way of like killing two birds with one stone.
Thank you.
Any more questions? Well, in that case, a round of applause.